x equals 0, it would be what boundary of a region? X equals 0. The x-axis, right? If you nodded, you're in trouble. The y-axis. All points where x equals 0, that's where you don't go left or right, right? So that's on the y-axis. And then y equals 0 is? Make sure you know that, okay? Make sure that you're confident with that. Because you can, like I said, you can miss several questions on the test if you choose y equals 0. If you choose the y-axis as y equals 0, and then your region's all wrong, and now you're missing a bunch on the test. Okay, so here's the one we're going to do today. We're going to sketch the region that's entirely in the first quadrant and is bounded by these three curves. 1/4 x squared plus 2, x equals 2, and y equals 6. So we're going to practice first. Can you figure out what region that's talking about? There's only, that's all the information you need to get one unique region. It's entirely in the first quadrant, and it's bounded by these three curves or lines only. It's not bounded by anything else. It's bounded by these three only. So see how you do. Okay, we'll start by practicing that. I'm going to take roll the old-fashioned way today. But we'll be doing it on Canvas normally. Let's turn these on. Did you get that for the curves? Yeah. So now there's all kinds of regions there that this could be, but there's only one that's entirely in the first quadrant and bounded by only those three. Is it this? Is it this? Is it this? Is it this? It's this. Is that what you got? This is the region right here. Y equals 1. Horizontal line or vertical line? Horizontal or vertical? Horizontal. There's our line of rotation. So now, can you draw the empty? Let's fill it in here. How about green? There we go. All right. So now, can we draw the empty shell you get when you rotate that thing around y equals 1? So this point right here around y equals 1, this is at what? Is this 3? So that point's going to be at -1, because it's 2 away from 1, so then we want 2 away from 1 is -1. This point's up at 6. That's 5 away from 1, so it's going to be 5 away from below 1, which will put it at, is that -4? This point also at, so this is at x equals 4 and y equals 4. So it's going to be x equals 4, 6. And then, so I think I'm here. So here where we are when we're halfway around in our revolution. Something like that. And now what, can you imagine what you get when you rotate that thing around that line y equals 1? What is it like? Like what? Like a non-functioning dog bowl or something? What will happen with this dog bowl?
It's a plate.
Everything will fall out the bottom, right? And so what is it? What's the empty shell that we're going to fill up? Is it this here? Exhibit A?
No.
Or is it the underneath there? Exhibit B. That, right? So the shell that we're filling up is this thing. Like if it's the dog bowl with a big hole in the bottom, up on its side, then it's actually the solid part of the dog bowl that we're going to fill up. That's our empty shell right now. Maybe that helps. Does that help? It's the best dog bowl I've drawn all day. Okay, so we're going to fill up this part, the outside part. Okay, so we're going to start with, we're going to do delta x intervals and let x vary through delta x intervals. Yes, sir?
So why do we do the section above the curve and not the section underneath the curve?
Here?
So like if the x was like this instead of like that, like why do we do the part above the curve instead of below it?
Are you saying why do we do this part up here and not something down here?
Yeah.
Because did you see why the region was the green one? That was before we even started revolving it. We got to get the fact that the region is the green region. Because that's the only one that met the criteria I said. It's bounded by all, that wasn't what I wanted. Bounded by all three of those entirely in the first quadrant. That's the only one that meets that. So down here, that has nothing to do with, say, y equals 6. This part.
I was just like, why would the 6 be the upper bound next here to do that shaded section kind of underneath?
Are you talking about here?
No, like if you were to stop, like for example, y right there would be 3. Like,
Y is 3.
yeah,
Yeah?
so like from there, go over to 4 and then up, like that section right there.
Then this whole thing is just a rectangle, has nothing to do with this curve then.
It would have been the area underneath the curve.
But then that has nothing to do with y equals 6. Then y equals 6 is not a boundary of it.
Upper bound of the curve.
So do you agree with these 3 blue curves right here? Do you agree with those 3, the parabola on the 2 lines? So this green section is the only one that fits what I'm saying, which is entirely in the first quadrant, bounded by those 3. So down here, is that what you're saying, all this? So maybe I'll just take a look at what you're drawing and we can answer that separately. Okay, any questions? So now we can do it. Hello. Okay, so now delta x intervals. And so you're going to imagine slicing this up into delta x intervals, and then we want to draw a typical cylinder like in the current delta x interval, okay? So maybe just make your delta x intervals here on the line y equals 1, and then for one of those, we want to sketch the cylinder that we get as a result of this rotation. Yes, sir?
When we, how do I put this? When we get the hollow shell, is the region that we are rotating going to be filled up if it were an object?
That's what we're going to do with the cylinders, right? So we always create the empty shell, and then we're going to fill it up with cylinders, and then the volume inside of the empty shell will accumulate as we fill it up with cylinders.
So the empty shell then is defined by the boundaries of that region rather than the region itself, right? And then the cylinders are defined by the region itself.
Yeah, so the empty shell is formed by the perimeter of the region.
Okay.
So the blue, right? So this blue, and then we're going to fill it up with cylinders. I just highlighted it green so we knew where we're going to fill up eventually.
Okay, thanks.
Yeah, it's an empty shell, and we're still working with the empty shell, and then we're going to fill it with cylinders. Yeah?
Less of a math question. How would you actually shape
So let's talk about that later. So let's move. Yeah, I'd love to help you with that, but gotta move forward. Okay, so So can you draw the typical cylinder that you'll get after x is varying through delta x intervals? So can you do that? Go. Okay, so this is what we think about. So if it's delta x intervals like this, then as we're going through a delta x interval, we would have, like just if we're talking about the original region, we just have this strip. So then how is this strip rotated? If the strip was rotated, what kind of cylinder would you get when you rotated that strip, which represents like x changing through a delta x interval? Yeah, it'd be a washer standing on its end. Do you see that? So you're going to get something like this. But the same thickness everywhere. So. Okay? Can you imagine that? So that's the cylinders that's going to fill this thing up. Those are the cylinders that's going to fill this thing up. Okay? Now imagine if x was changing through delta x intervals in the current interval, how would that cylinder be growing? Would it be growing in radius or would it be growing in height? Would it be growing in radius or height as x increased through delta x intervals?
Within the intervals, right?
Always within the interval.
Okay.
How does the current cylinder grow? It's not comparing the cylinders to each other. It's about at the current value of x. At the current value of x, how is the cylinder growing? Height. X is growing this way. The height is changing. Therefore, rate of change of volume is? Area of the base. Area of the base, some of you guys are saying it. And then in this case, the area of the base is? Pi r outer squared. We got a hole, right? We got a hole. So it's a circle area, but we got a hole. So it's going to be pi r outer squared minus pi r inner squared. Okay, and then so now we need to get what? We need to get these radii in terms of x. So I'm going to leave that to you. So when you're finding these radii and heights, when you're writing the rate of change function, the question always is it an x-coordinate, a y-coordinate, a big change in x, or a big change in y? It's always going to be one of those things. Is it an x-coordinate, a y-coordinate, a big change in x, or a big change in y? So see if you can find our outer and our inner. And then we got to write those, if they're not, we got to write those in terms of x, because that's our independent variable. Go. So you can do it. Inner radius. Did you get the inner radius? Okay, hold on. We're going to regroup. We're going to regroup. Here we go. We're bringing it back to the front. So that inner radius, first of all, let's answer the question. Is it x-coordinate, a y-coordinate, a big change in x, or a big change in y? Change in x, the inner radius. Agree with that? It's a change in x, that radius. Change in y, right? Lots of you are nodding your head. No, this is a change in y, right? This is a change in the vertical coordinate, not change in x. Changes in x's go this way, right? So this is a change in y. Okay, and so how do we calculate that change in y? It's going to be, how far is that from there to there? Oh, this is inner, sorry. I'm doing the inner radius first here. So it's going to be this minus this, right? So it's y final minus y initial. And what is y initial? 1, right? So the distance from here to here is the y-coordinate of the inner radius. And what's the y-coordinate going to be? This y-coordinate, right? Minus 1. So y final minus y initial gives change in y. All right, so we'll change that later. Then what about the outer radius?
That's always 5.
That's always 5.
Because y final in that case is always 6, and then you're just subtracting y initial, which is
Right.
always 1.
Right, so it's going to be 5 minus 1. 6. So we're talking about the outer radius. The outer radius is always from 6 to 1 on these cylinders. So it'll be 6 minus 1. This y-coordinate is the y-coordinate of the curve, right? So our rate of change will be pi times 5 squared minus pi times
1/4 x squared plus 1.
So this is the y coordinate, y coordinate of the inner radius to the, or where that inner radius stops, to the center of rotation is 1. So there's our rate of change. Okay, and we know how to, so we're going to write the accumulation function, but I'm going to actually just type those into GC. So we'll stop here on this one. Now we're going to chop this up into delta y intervals and let y vary through delta y intervals. Okay, first sketch the empty shell, and then if you're good on that, you can do the rate of change function. Okay, but first sketch the empty shell you're going to get when you let y vary through delta y intervals. So that's going to start here and go to here. So here's our delta y interval, something like this. So there's your delta y intervals going through that region. So first start with a strip. Imagine what you get when you revolve the strip. And that's the cylinders that we'll have. Draw the cylinder, figure out the rate of change. Is the task clear? Okay, so imagining y changing through delta y intervals, delta y interval would be like this, and then y would be growing through the delta y interval, and we'd be forming kind of strips like this, and when you rotate those strips around y equals 1, what do you get? So imagine that thing rotating around, so then at halfway it's something like this. So what's that going to be like? It's going to be like a sleeve or a shell, something like that. So this is now y is an independent variable. This was x up here. All right, and then as y varies through the current intervals, y is varying. How is this particular shell growing? In height or in radius? Radius. Good. You should be seeing that as y grows this way, this thing is increasing in radius. Therefore, rate of change is rate of change of volume with respect to y. Surface area of the rounded side. Surface area of that I shaded. That's the face that's growing, or where the accumulation is happening. So that size of that is the rate of change. And what is that? 2 pi rh, circumference times the height. Remember that? There's 2 in these cylinders that grow. If they grow by height, the rate of change is the area of the base. If they grow in radius, the rate of change is 2 pi rh. So now we got to ask, this radius and this height, we're going to ask the question, is it an x coordinate, a y coordinate, a big change in x, a big change in y, excuse me. Remember, this is y equals 1. To get this shell, we rotate about y equals 1. So what about the radius? Is it x coordinate, y coordinate, big change in x, or big change in y? Big change of y, right? It's not quite a y coordinate because it's not from y equals 0. It's from y equals 1. So it's going to be the change in y from the edge of the cylinder to the center of rotation, which is 1. All right, so it's going to be 2 pi y minus 1. It's whatever y is, right? So as y changes through here, our independent variable y? Whatever the current value of y is, that's the y coordinate of the edge of the shell. So then it's just y minus 1 is the radius. What about the height? Is it x coordinate, y coordinate? Big change in x, big change in y. It's a change in x. It's not an x coordinate because it's not from y equals 0, right? X coordinates are from the y-axis. So it's a big change in x because it's from, what, x equals 2. So it's going to be big change in x. Final x is, we'll figure that out in a second, minus initial x. 2. So what are we rewriting? We have to rewrite x in terms of y. So we need what? We need the x coordinate along here, right? So it's the x coordinates along that curve in terms of y. How do we find that? So I need x in terms of y for the curve. What does that entail? What do I have to do? Yeah, I gotta do the algebra on this to solve this for x. So I get this because it's the x coordinate on this curve, but we need to write it in terms of y. So it's going to be y minus 2 first, right? Solving for x, then we're going to multiply by 4, and then we're going to square root it. Okay, so it's x is actually 2, and move that 4 out as a 2. 2 times the square root of y minus 2, and that minus 2. Yes, sir?
You would have to subtract like the iterating somehow, right? I'm not clear where that operation takes place.
Tell me what part of this?
Or, because in the middle we had like an outer thing and
Right.
the inner radius.
Right?
We have to do the same thing.
Nope. The rate of change when you have a cylinder growing in radius is 2 pi rh. It's all about the rate of change. Remember? When cylinders grew in height, the rate of change is the area of the base. When cylinders grow in radius, the rate of change is 2 pi rh, the area of this shaded region. So now this is my rate of change. This is the whole ball of wax. If I want accumulation of volume, I need rate of change. So now I need to write this in terms of y and this in terms of y. And I got it, the rate of change function. It's all about the rate of change function. If you want accumulation of volume, you need the rate of change function. And when we spent a whole day coming up with these formulas, that when the thing grows in height, it's the area of the base. When the thing grows in radius, it's 2 pi rh. It's this area where it's growing. We're not finding the volume of these cylinders. We're not finding the volume of these cylinders. We're writing what the rate of change is for these cylinders. Okay, other questions? Okay, so let's write down the two accumulation. So write down your accumulation functions. Write down, we'll call this V1. So V1 is when we do it in terms of x, V2 in terms of y. Go. Write down the accumulation of volume as the cylinders fill the shell, whether it be the x cylinders, that'll be your V1 function, or the sleeve cylinders. Write down the accumulation functions. Go. Have they been written down? Maybe.
Yeah, but it's not like
Yes.
you're starting from two.
Okay. This is what I have for V1. Is this right? Or is that, does it agree with what we came up with, is what I'm asking. That's what you should have written for V1. Because so what would this be? This would be V1 of what, normally? V1 of 2. But there's no accumulated volume before x equals 2, so it's 0. So yeah, so if you wrote V1 of 2, that's good. V1 of 2. But that's 0, so that's why I have 0. Okay, V2? It's this one. Does that agree with what we did? What would this be in function notation?
V sub 2 of 3.
3. V2 of 3. Okay, now I want you to represent the volume of the entirely filled shell, so the whole solid, in two different ways. Represent the volume of the whole solid in two different ways. Okay. Where's Matthew B? Matthew B. Where's Matthew? Yes, sir. Okay. So did you find one way to represent the volume of the whole filled shell? No? Yeah. She wants V1 of 4. Does it work? So V1 is accumulating starting from x equals 2 and accumulating this way. And so then I assume is the x coordinate of that point 4? Good. You'd have to find the x coordinate of that point when we finish filling up the empty shell. That's x equals 4. So then we want V1 of 4 represents the whole volume. And then we let GC do the work for us. And it's 85.5192. Okay, another way to represent the volume of the whole shell. Angel, did you get it?
Yeah.
Tell me. The other way to represent the volume of the whole filled up shell. You didn't get the other one? Yeah. Eli.
I think it's the definite integral between 2 and 4 of RB of T dt.
Okay, can we do it in a more concise way? So yeah, you could use the integral, but what about something like this? Something super simple. Yeah. V2 of 6. Agree with that? Yeah, because of V2, we're start accumulating here. We're going to accumulate until, if we want the whole thing filled up, then we want the last y value, which is 6. So V2 of 6, what do you notice? Same. Totally different functions, right? Totally different functions, but they're just filling the shell in a different way, but when they get done filling the shell, it's the same volume, right? It's the same volume. Okay, so what about V2? So what is y starting at? 3? 3 to 6? So halfway is 4.5. What about V2 of 4.5? Is that going to be half of the volume? I'm going halfway up in y. More or less? Less, a lot less, for two reasons. Why? Because all this stuff has a shorter distance to go in its rotation, and we got more of the region out here, right? Our cylinders have a bigger height. So we should think that V2 of 4.5 is a lot less than half. Two reasons. That lower part of the region has a lot less distance to travel than the outer part, and then the outer part has bigger heights on those cylinders. So way less than half. Okay, what about halfway on x? So x goes from 2 to 4. What about V1 of 3? Is it going to be half of the volume? More or less? This is more because that inner radius, or we got a lot more stuff here for low values of x than we do for high values of x. So V1 of 3. Oh, right, so if we really want half, right? If we really want half of the volume, we should take all the volume and divide it by 2. If we do V1 of 3, it's clearly more volume because the difference between the inner and outer radius is a lot greater for those lower values of x. Okay, so lots to these problems, and you got to know it all for the test. You got to know it all. You got to know how to form the empty shell. You got to know how to draw or imagine cylinder. You got to know how to write the rate of change function. Are you listening? You got it. Excuse me. You got to know how to write the accumulation function. Then you got to know how to use function notation to represent values of volume as that thing's being filled. Question? Yeah, actually, you can have a basic calculator. There's just a couple problems where you may have to do some calculations, but like everything we did today didn't require a calculator. That's most of the test.
What will the